Calculate the solubility parameter of polyisobutene from table 3.3. How does this value compare with that shown in figure 3.2? Polyisobutene is CCH3, CH3, so this is polyisobutene. Solubility parameter formula is given as delta equals rho, where rho is the density, sigma g, where sigma g is the sum of the molar group attraction constants, over n, where n is the molar mass. From table 3.2, we can see the density of polyisobutene is 0.917 grams per centimeter cube. Sigma g we can pick from table 3.3, and the group molar attraction constant for methyl is 214. There are two methyl groups, 1 and 2, so it will be 2 times 214 plus there's one carbon with 4 single bonds, and for that the value is negative 93, and then we have one CH2, for that the value is 133. If we add all this, we get 468. The units for G is given as square root of calories centimeter cube per mole. Let's find the molar mass. There are 4 carbons, 4 times 12 is 48, and there are 8 hydrogens, 8 times 1 is 8, so we have 56 grams per mole. Plugging all these values, we can find delta. Which is 7.66 square root of calories per centimeter cube. So if we compare this value with the value in figure 3.2, in figure 3.2 we can say that the value of delta for polyisobutene is close to 8, is approximately equal to 8 square root of calories per centimeter cube.
What is the free energy of mixing 1 mole of polystyrene, molecular weight 2 times 10 to the 5 grams per mole, with 1 times 10 to the power 4 liters of toluene at 298 Kelvin? So free energy of mixing delta G is given by delta Gm is kT times N1 ln V1 plus N2 ln V2 plus chi N1 V2, where K is a Boltzmann constant, T is the temperature, N1 and V1 are the number of molecules and volume fraction of the solvent. N2 and V2 are the number of molecules and volume fraction of the polymer. Chi is the Flory-Huggins parameter for the given solvent polymer. So let's find Kt. K is 1.38 times 10 to the negative 23 joules per mole, and temperature is given as 298 Kelvin. So Kt equals 411.24 times 10 to the negative 23 joules. So we have 10 to the power 4 liters of toluene, which is 10 to the power 7 milliliters or 10 to the 7 cubic centimeters of toluene. Molar mass of toluene is 7 carbons, so 7 times 12 is 84. 8 hydrogens, so 8 times 1 is 8, so it's 92 grams per mole. Density of toluene from table 3.2 is 0.8669 grams per centimeter cube. So mass of toluene is density times the volume, so it's 0.8669 grams per centimeter cube times 10 to the power 7 centimeter cube, which is 10 to the power 7 times 0.8669 grams. Number of molecules of toluene would be the mass divided by the molar mass, which is 92 grams per mole, times 6.023 times 10 to the 23 per mole, which is the Avogadro number. So the number of molecules comes to 567.5 times 10 cube times 10 to the 23 molecules. So this is N1. Total volume of toluene and polystyrene is volume of toluene plus volume of polystyrene. Molecular weight of polystyrene is given as 2 times 10 to the power 5 grams per mole. Density of polystyrene from table 3.2 is 1.06 grams per centimeter cube. So number of moles of polystyrene is given as 1 mole. So mass of polystyrene is 2 times 10 to the power 5 grams per mole times 1 mole, which is 2 times 10 to the power 5 grams. So volume of polystyrene is mass over density, which is 2 times 10 to the power 5 grams over 1.06 grams per centimeter cube, which is 188,679 centimeter cube. So the total volume is 10 to the power 7 centimeter cube of toluene plus 188,679 centimeter cube of polystyrene, which is 10 to the power 7 times 1 plus 0.019 centimeter cube, which is 1.019 times 10 to the power 7 centimeter cube. So this is a total volume V1, that is volume of toluene, which is 10 to the power 7 liters over the total volume, which is 0.98. So V1 equals 0.98. So V2 is the volume of polystyrene, which is 188,679 milliliters over the total volume, which is 10 power 7 milliliters, and that is 0.019. So V2 is 0.019. N1 is 567.5 times 10 cube times 10 to the 23 molecules times ln V1 is ln 0.98, and that is negative 11455 times 10 to the 23. N2 ln V2 would be number of molecules of polystyrene is 6.023 times 10 to the 23, since it's just 1 mole, times ln V2 is ln 0.019, which is negative 23.87 times 10 to the 23. Chi N1 V2 is, value of chi from the table is 0.37. So 0.37 times N1, which is 567.5 times 10 cube times 10 to the 23, times V2, which is 0.019, and that is 3990 times 10 to the 23. Now delta G of mixing is Kt times N1 ln V1 plus N2 ln V2 plus chi N1 V2. So Kt was 411.24 times 10 to the negative 23. N1 ln V1 is negative 11455 times 10 to the 23. N2 ln V2 is negative 23.87 times 10 to the 23, and chi N1 V2 is 3990 times 10 to the 23. 411.24 times that gives us 3080 kilojoules. What is the molecular weight of a 10-gram rubber band? Rubber band is a copolymer of butadiene and styrene, and it is cross-linked. Assuming that the whole rubber band is just one molecule of cross-linked copolymer, the mass of the rubber band is equal to the molecular weight of the rubber band. What are the K and A in the amark-Houwink Sakurada equation for polystyrene in benzene from figure 3.15? So figure 3.15 gives the double logarithmic plots of eta versus log mw. It is for anionically synthesized polystyrene, which is fractionated, and the values of mw over mn is less than 1.06. So it has a narrow molecular weight distribution. The filled circles in benzene and the half-filled circles are in toluene, and open circles are dichloroethane, ethylene. Since we are concerned with benzene, we want to look at the filled circles, which is the topmost straight line, all at 30 degrees centigrade. The arrows indicate the axis to be used. For the top line, the x-axis is on the top and the y-axis is on the left side. Let's write the equation. Amark-Houwink equation is log of eta equals log k plus a log mv. Since the weight distribution is narrow, we can assume the viscosity average molecular weight to be close to the weight average molecular weight. So we can take it as log eta equals log k plus a log mw, since molecular weight distribution is narrow, since it's mw over mn is less than 1.06. Okay, so if we look at the graph, we want to find out the slope and the y-intercept. A is the slope and the y-intercept is log k. And A and K are the amark-Houwink's constants, which we want to find.
Okay, so let's pick 2 points on this straight line. So I have picked 2 points. P1 equals, you could pick any 2 points. The x coordinate is 6.25 and the y coordinate is 0.6. And for P2, the x coordinate is 5.375, the y coordinate is 0.0. So the slope is the difference between the y coordinates over the difference between the x coordinates. So that is 0.6 minus 0.0 over 6.25 minus 5.375, which gives a slope of 0.686. So A equals 0.686. Coming to the y-intercept, so let us write the equation. The equation would be y equals slope 0.686 times x plus b, where b is the y-intercept. If we take the same point P1 and substitute these values, y is 0.6 and x is 6.25 plus b. So b equals negative 3.69, which means log k equals negative 3.69 and k equals 2.0 times 10 to the negative 4. A trifunctional carboxylic acid monomer is being reacted to form a polyanhydride. What is the critical extent at gelation? The critical extent of reaction at gel point is given by Pc equals 1 over F minus 1 square root of that, where F represents the functionality and F is greater than 2. So this is the Flory-Stockner equation. Since it's a trifunctional carboxylic acid, we can substitute 3 for F, and solving for Pc we get Pc equals 0.71.
A 5 gram sample of a polyester having 1 carboxylic group per molecule is to be titrated by sodium hydroxide solutions to determine its number average molecular weight. How much 0.01 molar solutions is required if the polymer has a molecular weight of approximately 1000 grams per mole, 10,000 grams per mole, 100,000 grams per mole? Discuss the practicality of the experiment with special reference to the upper molecular weight limit that can be analyzed. So mass of the polyester is 5 grams. Let us consider the molecular weight of 1000 grams per mole. So the number of moles of the polyester would be 5 over 1000, which is 0.005 moles. Since one carboxylic acid group is present per molecule, we'll have 0.005 moles of carboxylic group. To titrate 0.005 moles of carboxylic group using 0.01 molar solution of alkali, we'll need 0.005 moles over 0.01 molar, which is 0.5 liters. So we'll need 0.5 liters of sodium hydroxide will be needed. So for 1000 grams per mole, we need 0.5 liters, which is 500 milliliters. For a molecular weight of 10,000 grams per mole, the number of moles will be 5 grams over 10,000, which is 0.0005 moles, and that would have 0.0005 moles of carboxyl group. So for a 0.01 molar alkali, we'll need 0.0005 moles over 0.01 molar, which is 0.05 liters, or which is 50 milliliters. For 100,000 grams per mole molecular weight, we can similarly show that we need 0.00005 moles of carboxyl group to be titrated, which will require, let's write this as 5 times 10 to the negative 5 moles, which will require 5 times 10 to the negative 3 liters, which is 5 milliliters. So we can see that as the molecular weight increases, the volume of 0.01 molar sodium hydroxide needed decreases, and at 100,000 grams per mole of molecular weight, the volume needed is 5 milliliters, and 5 milliliters is too less to perform titration accurately. So it's practically not feasible or not possible to get good results for this high molecular weight polymer. So if we assume that we need at least 25 milliliters of sodium hydroxide, assuming that we need at least 25 milliliters of NaOH to perform a good titration, that would be 0.025 liters of NaOH, so which would be 0.025 liters times 0.01 molar, which is 0.00025 moles. So this is the moles of polyester that would be needed to titrate, and that would correspond to, for a 5 gram polyester, that would correspond to a molecular weight of 20,000 grams per mole. So we can say that maybe an upper limit of 20,000, approximately 20,000 grams per mole of polyester, of a 5 gram polyester, can be analyzed using this method of titration.
What are the enthalpy of vaporization and enthalpy of fusion based on table 3.5, assuming boiling point is 150 degrees centigrade and freezing point is 10 degrees centigrade and density is 1.0 grams per centimeter cube. For dilute solutions, delta TB, the elevation in boiling point, over C, where C is the concentration, is given by R, the universal gas constant, times T squared over rho delta HB times 1 over Mn. R is the universal gas constant, 8.314 joules per mole per Kelvin. T is the temperature, rho is the density, delta HB is heat of vaporization in joules per mole, Mn is the number average molecular weight of the polymer, and Tb is the elevation in boiling point. So rearranging, we can get delta HB equals RT squared over rho times delta TB times C over Mn. We can plug in the values. Temperature is 150. In Kelvin it would be 150 plus 273. Concentration is 1%, so 1 over 100 grams per centimeter cube over density is 1.0 grams per centimeter cube times delta TB is 1.3 times 10 to the negative 30 Kelvin and Mn is 20,000 grams per mole. So we get delta HV in joules per gram, 57.22 times 10 to the 28 joules per gram. For the freezing point depression, similarly, delta TF over C equals minus RT squared over rho delta HF times 1 over Mn, where delta TF is the freezing point depression, C is the concentration given as 1%, R is the universal gas constant, T is the freezing point in Kelvin, rho is the density delta HF is the heat of fusion, and Mn is the molecular weight of the polymer. Delta HF equals negative RT square C over Rho 1 over Mn. Temperature is 50, temperature is 100, which is 100 plus 273 Kelvin. That gives delta HF as negative 2.31 times 10 to the 29 joules per gram. Since the delta HF value is in the order of 10 to the 29 and delta HV is in the order of 10 to the 28, colligative properties and polymers for elevation and boiling point and depression and freezing point are very, very minimal. This is the molecular weight of the cellulose tricaproate sample in figure 3.5. Note R equals 0.08205 atmosphere liter per mole Kelvin for this problem. Figure 3.5 is a plot of pi by C versus concentration for cellulose tricaproate in dimethyl formamide at three different temperatures: 53.5, 41.6 and 30.0 degrees. It is said that the Florey theta temperature was determined to be 41 plus or minus 1 degree centigrade. So let's write the equation. Pi by C equals RT times 1 over Mn plus A2C. And A2 is the second virial coefficient. So at theta temperature, A2 is equal to 0. So pi by C becomes equal to RT over Mn. If we see the figure, at 41.6 degrees centigrade, the straight line is almost parallel to the x-axis, and it says that the Florey theta temperature is determined to be 41 plus or minus 1. So we can take the straight line at 41.6 as the straight line at Florey theta temperature, and this intersects the y-axis at 1.9, which means at Florey theta temperature, the pi by C value is 1.9 times 10 to the negative 4, because the y-axis is given in terms of pi by C times 10 to the power 4. So the number denoted on the y-axis should be divided by 10 to the power 4. So we get 1.9 times 10 to the minus 4 atmospheres per gram per liter. R is 0.08205 liter atmospheres per mole Kelvin, and T is 273 plus 41, which is 314 Kelvin. So with all this, we can try to find out the molecular weight. So the molecular weight comes to 135,598 grams per mole.
What are the units for A2 in both CGS and SI unit systems? So we have pi over C is equal to RT over Mn plus RT A2C, which means units of RT over Mn and RT A2C should be the same since we are adding them, and that should be equal to the units of pi over C. Now, since units of RT over Mn and RT A2C should be the same, we can cancel RT on both sides. We can say units of 1 over Mn and A2C should be the same, which means units of A2 should be equal to that of 1 over MnC. And in SI, units of A2 would be 1 over, for molecular weight it will be kilogram per mole, times for concentration it will be kilogram per meter cube. So which would be mole meter cube by kilogram squared. So this will be in SI. So in CGS, this would be mole centimeter cube over gram squared. What is the estimated radius of gyration of a 5 times 10 to the power 5 grams per mole polystyrene in the bulk state? From amark-Houwink equation, we know that eta equals km to the power a. K is given as phi r0 squared over m to the power 3 by 2, where r0 is the root mean squared, end-to-end distance of the unperturbed coil. Rg, the radius of gyration, is related to the distance between ends of the chain for random coils as Rg squared equals r squared over 6 times, where r is equal to distance between ends of chain for random coils. So we can approximate R0, the root mean square distance, to be R. In a theta solvent, polymer behaves as in the bulk. we can substitute the radius of gyration for r, and we can say k equals 5 times 6 rg squared over m times 3 by 2, which means rg equals km to the power 3 by 2 over 5 times 6 to the power 3 by 2 the whole 1/3. K can be found from the table, and it is 84.6 times 10 to the negative 3. Phi is a constant given as 2.5 times 10 to the 21 deciliters per mole centimeter cube. Molecular weight m is given as 5 times 10 to the power 5 grams per mole. So plugging in all these values, Rg equals by calculating, we find that Rg equals 9.3 times 10 to the negative 6 centimeters. The intrinsic viscosity of a sample of polymethyl methacrylate in acetone at 20 degrees Celsius was found to be 6.7 milliliters per gram. What is its viscosity average molecular weight? We know from the amark-Houwink's equation, eta equals kmv to the power a, where eta is the intrinsic viscosity, k is a constant, mv is the viscosity average molecular weight, and a is a constant. From table 3.10, we see that for polymethyl methacrylate in acetone at 20 degrees centigrade, the value of K is 5.5 times 10 to the negative 3, and the value of A is 0.73. So plugging this in the equation, we can get 6.7 equals 5.5 times 10 to the negative 3 times m to the power of 0.73. We get a viscosity average molecular weight of 16,879 grams per mole.
Prove the relation K prime plus K double prime is 0.5, which is the equation 3.103. So we have eta specific by C equals eta plus K prime eta squared C. This is equation 3.101. And then ln eta relative by C equals eta minus K double prime eta squared C. This is equation 3.102. So if we subtract equation 3.102 from 3.101, we can cancel eta and we get eta specific by C minus ln eta relative by C equals K prime plus K double prime times eta squared C. So we did this so that we can get the K prime plus K double prime factor. Ln eta relative is also given as ln eta specific plus 1, which is approximately equal to eta specific minus eta specific squared by 2 plus so on, and that's equation 3.87. So plugging this in the previous equation, we can say eta specific over C minus 1 over C times eta specific minus eta specific squared over 2 equals K prime plus K double prime times eta squared C. So we can cancel this. Then eta specific over C at C is equal to 0 is eta, giving K prime plus K double prime is equal to 0.5.
What is the Z-average molecular weight of the polymethyl methacrylate shown in table 3.13? The polymethyl methacrylate shown in table 3.13 is synthesized by radical polymerization. For a random molecular weight distribution, such as that which is produced by free radical polymerization, the molecular weight distribution is like that shown in this graph, where the y-axis is the weights, Wi, and the x-axis is the molecular weight of the species. So this is Mn, this is Mw, and this is Mz. For a random molecular weight distribution, Mn is to Mw is to Mz is 1:2:3, as shown in this illustration. In the table, we see that Mn equals 4.01 times 10 to the power 5 grams per mole, and Mw equals 8.82 times 10 to the power 5 grams per mole. So Mn and Mw are approximately 1:2. So Mz will be 3 times 4.01 times 10 to the power 5, which is 12.03 times 10 to the power 5, or 1.2 times 10 to the power 6 grams per mole.
Given the following data, what is the number average molecular weight and the second virial coefficient? T is 25 centigrade and density is 1.0 gram per centimeter cube. So first we draw a best fit straight line through the points. I've done that, and then we pick 2 points on the straight line to find the slope. Y-axis, you see that it says pi by c times 10 to the power 3, which means the point on the y-axis should be divided by 10 cube. So the 2 points that I'm picking are P1 is 0.02 on the x-axis, and on the y-axis it is 0.29 times 10 to the negative 3. Another point I'm picking on the y-axis itself, so the x-coordinate is 0 and the y-coordinate is 0.25 times 10 to the negative 3. So the slope of this is the difference in y-coordinates over the difference in x-coordinates. So that is 0.29 times 10 to the negative 3 minus 0.25 times 10 to the negative 3 over 0.02 minus 0.00, which is 0.002. So we have the slope. The equation for this straight line is pi by c equals RT times 1 over mn plus A2C. Mn is the molecular weight and A2 is the second real coefficient. So the plot is pi by c versus c. So the slope will be equal to RT A2 and the y-intercept is RT over Mn. Since we have found the slope, we can plug in the values to find A2. A2 will be slope over RT which is 0.002 over 0.08205 times 298, because the temperature is 25, so 273 plus 25 is 298 Kelvin. That gives A2 a value of 8.18 times 10 to the negative 5 moles centimeter cube per gram square. Now y-intercept is equal to RT over Mn, and the y-intercept is, from the graph we can see that y-intercept is 0.25 times 10 to the negative 3. So plugging these values, Mn equals 97,804 grams per mole.
A new polymer has intrinsic viscosity of 5.5 cm cube per gram and an elution volume of 160 cm cube. Based on the method of figure 3.23, what is the molecular weight? Figure 3.23 is a universal calibration graph of eta m, where eta is intrinsic viscosity and m is the molecular weight, versus the elution volume in a GPC. It is based on the understanding that the elution volume in GPC depends on the polymer's hydrodynamic volume. Now, we know from amark-Houwink Sakurada equation that eta times m equals phi r0 squared to the power 3 by 2 times alpha cube, where r0 is the root mean square distance, root mean square end-to-end distance of the polymer chain. So, the quantity on the right, which is phi r squared to the power 3 by 2 times alpha cube, is proportional to the polymer's hydrodynamic volume. So we can say that the molecular weight is proportional to the polymer's hydrodynamic volume. And this is the basis of GPC, in which the elution volume is indicative of the polymer's hydrodynamic volume. So in this graph, we see that on the y-axis we have eta times mr, and on the x-axis we have the elution volume. So if you observe the y-axis, the values are 10 to the power 4, 10 to the power 5, 10 to the power 6, 10 to the power 7, and so on, which means that the y-axis is actually the log values, so that if you find the log of 10 to the power 4, it will be 4, 10 to the power of 6 is 6, 10 to the power of 7 is 7. Okay, so we can read them as the log of eta mv on the y-axis. Distance between the adjacent points is 1. On the x-axis we have the elution volume, and this is given as V over 5 centimeter cube, which means you have to multiply the volume as denoted on the x-axis by 5. So if it is 30, then it would be 30 times 5, 150 centimeter cube would be the elution volume. So the line is like this. The eta given to us is 5.5 centimeter cube for an elution volume of 160 centimeter cube. So 160 centimeter cube would correspond to 160 divided by 5, which is 32, and that corresponds to eta of 5.5. So we have to find the point on the y-axis that corresponds to 32 on the graph. So if you look at the graph, the original graph, and if you find out what the y coordinate of this point is, we'll see that it matches with the value of 5.2. So when I did that, I found that this value here, it matched at 5.2. So let's plug this in. Log of intrinsic viscosity times molecular weight is equal to 5.2, which means log of eta plus log of m equals 5.2. So log of m is equal to 5.2 minus log of eta, which is 4.6. So log m is 4.6. So m is equal to 28,816 grams per mole. So that's the molecular weight.
What are the solubility parameters of the polyurethane and polystyrene in figure 3.1? Figure 3.1 is a plot of the swelling coefficient of the polymer on the y-axis and the solubility parameters of various solvents on the x-axis. The polymer is treated with different solvents of different solubility parameters, and a graph is plotted of the swelling coefficient of the polymer on the y-axis with the solubility parameter on the x-axis. The swelling is maximum when the solubility parameter of the polymer matches with the solubility parameter of the solvent. So, if we have a graph like this, in which Q is the swelling coefficient on the y-axis and delta is the solubility parameter on the x-axis, and if I get a graph like this, then the solubility parameter of the polymer is at the peak. It is where the swelling coefficient is a maximum. That is the solubility parameter of the polymer because it is closest to the solubility parameter of the solvent. For polyurethane, delta would be the one with squares, so the peak is at, it matches at 21.75 times 10 cube because the delta values are given in terms of 10 to the negative 3, so the value on the x-axis has to be multiplied by 10 cube. Similarly, for polystyrene, the peak is at 18, so which means delta is 18 times 10 cube joules to the power half m to the power 3 by 2. For the interpenetrating polymer network between polyurethane and polystyrene, the peak is at 20, so delta is 20 times 10 cube joules to the power half m to the power 3 by 2. We tend to think of molecules as being of finite size. The polymer networks used in figure 3.1 are clearly the size of the sample, while the molecules used in figure 3.2 are clearly finite and soluble. In what philosophical sense are or are not the materials making up figure 3.1 molecules? The molecules in figure 3.2 are cross-linked. They are cross-linked polyurethane, cross-linked polystyrene, and interpenetrating networks of polyurethane and polystyrene. Technically, they are molecules because all the atoms in the polymer network are covalently bonded. It is kind of a paradox because molecules are generally of the order of angstrom or nanometers in size and are not visible to the naked eye. They can only be seen under powerful electron microscope. So that polymer networks could span the entire sample size as one molecule.
Two syntheses of the polymer are made, but with different molecular weights Ma and Mb with the intrinsic viscosities eta A and eta B. Derive general equation to express the intrinsic viscosity of various blends of the two syntheses as a function of composition. Viscosity average molecular weight is given as Mv equals sigma Ni Mi to the power 1 plus A over sigma Ni Mi the whole to the power 1 over A, where A is the amark-Houwink's constants. So this is the viscosity average molecular weight. This can be written as sigma Ni Mi to the power A over sigma Ni Mi the whole to 1 over A. If Wi equals NiO times Mi, the weight of the species, then Mv equals sigma Wi Mi to the power A over Wi the whole to 1 over A. Since the polymer blend has molecular weights Ma and Mb, and if Wa and Wb are the weights of polymer Ma and Mb, then the viscosity average molecular weight is Wa Ma to the power A plus Wb Mb to the power A over Wa plus Wb. The whole to the power 1 over A. Also, we know that intrinsic viscosity is Km to the power of A. So, the intrinsic viscosity of this blend can be given as K times this Wa Ma to the power A plus Wb Mb to the power A, Wa plus Wb to the power 1 over A times A. Now we can also plug in eta A equals Km A to the power A and eta B equals Kmb to the power A. So if we do that, the viscosity of the blend is K times, this becomes 1, Wa, we can substitute Ma for eta A over K plus Wb times eta B over K Wa plus Wb. So K gets cancelled and we have the viscosity of the blend as Wa eta A plus Wb eta B over WA plus WB. So WA was equal to Na times molecular weight of A. So we can substitute that. So Na Ma eta A plus Nb Mb eta B, Na Ma plus Nb Mb